Hello, my name is Luc McCutcheon. I'm a PhD researcher at CAV-Lab at the University of Surrey. And in this paper, we're proposing an adaptive PD controller, which uses time-delayed deep reinforcement learning to choose appropriate PD gains for the task of synchronizing a local remote robotic arm system. So in this presentation, I'm going to cover 4 key concepts. So I'm going to introduce this adaptive PD controller and the task that we're trying to achieve. And then I'm going to introduce action buffer-based state prediction, a common approach to underlaying an environment to be used in reinforcement learning, and state buffer-based state prediction. So it's an improvement for our model-based reinforcement learning approach. And predictive model delay correction. So this is the overall algorithm which uses SBSP at the end there. So in our local remote system, the operator will take an action and receive an observation. And essentially its position and velocity is then used to update the observation of the remote agent. So this setup has 2 parallel gym environments where all of the object information is removed from the remote and replaced with position and velocity of the end effector of the local system, the operator. We then apply observation delay to the observation and then choose P and D controller gains using PMDC or our soft actor-critic variant, and then apply action delay at the end of it before it's applied to the remote environment. So what is ABSP? So essentially, one approach to predicting future underlaid states is to use a neural network and essentially take in the current state and action as input and predict the next state. So if there's a time delay of 8, you can see this happening sort of 8 times iteratively for each time step in an episode. And essentially this is very time consuming. So what we propose is to sort of save previous predictions and kind of have a current future state in the future, which we're using as our underlaid observation. And then we simply each time step apply our action from PMDC using the forward model to then get the next time step and use that in RL. So by saving these predictions, we're able to essentially just do one inference per time step to achieve the underlaid state. The problem with this is that the error accumulates over time. So because we're sort of bootstrapping our predictions from the beginning of the episode towards the end of the episode, it's been so long since it's seen a real observation that it can be kind of way off. And so to stop this, we use a recalibration step where essentially we find the difference between the true state when we encounter it and our previous prediction of what it was. And then we take that error away from all of the states in the future state buffer. Yeah, and as part of PMDC, we also use an ensemble model just to kind of make the training more robust and accurate, particularly as the model is learning at the beginning. So as we can see from the results, SBSP is far more efficient than ABSP. So our proposed method of reusing predicted states allows the training and inference time to be so much quicker, and it also performs far better than the other approaches for longer delays. This is because ASAC, the augmented soft actor-critic approach, appends a action queue to the state space for the entire for the maximum amount of delay possible. So in the longest delays we experimented with, that'd be 29 time steps, 29 actions appended to the observation, whereas in PMDC we only use over the stochastic range, which would be about 40 milliseconds. So this curse of dimensionality is why ours performs far better as the delay increases. And finally, I just wanted to say a big thank you to University of Surrey and Veolia for sponsoring this research.